But what we're going to do now is we're going to look at evaluating limits. Evaluating, and you'll be doing this for homework, limits. Now the easiest kind of limit to evaluate is when your limit is a polynomial, which is so nice. So we say the limit as x approaches c of a function, and I'm going to put in this formula for a standard polynomial. It's lead coefficient a sub n times x to the n. I hope this is familiar. So this is a degree n polynomial written in standard form. The next term would be the second coefficient a sub n minus 1 times x to the n minus 1, and we keep on going until we get down to finally our constant term. Okay, and in this case, this limit is going to simply be the value of the function if you substitute in a c for x. Okay, so if this is the limit as x approaches c of f of x, where f of x is this function that I just wrote, then the limit is going to be f of c. I'm going to move this over. I've given myself not enough room. So the limit will be f of c because it's a polynomial. So this is when we have polynomials, and this is lovely. Polynomials are so easy. When we're resolving limits for polynomials, we merely substitute in c for x. And a polynomial is smooth and continuous. Yes?
It's supposed to be f of c.
Oh, thank you so much. Oh, made a mistake. Let's fix that. Thank you, Stephen. Okay, so, and I just want to write this in because this is like important for calculus. Polynomials are smooth and continuous. They don't have breaks in them. That's really important. So I'm writing that in red because it will show up when we start working on the derivative. Okay, so we start to have things start to change when we're dealing with polynomial functions that when we're dealing with limits that are on things that are not polynomial functions, okay? So we're going to take, what about this one here? I'm going to do a ratio. The limit as x approaches 0 of the tangent of x over x. And the problem here is you can't just substitute in 0. Let me move this over. Because you'll have a divide by 0 error, right? And the tangent is the sine over the cosine. So the tangent of 0 is 0, because the sine of 0 is 0, and the cosine of 0 is 1, and 0 over 1, so it's 0. So the tangent of 0 is 0, but we still have a divide by 0 error. So what we have to do is we have to pull this apart. So this is where we have to start doing a little bit of work in limits. Now we could also graph it and look at it graphically to see what it looks like. But in this case, we would separate it out, and we know that the tangent is the sine of x over the cosine of x. That's the tangent, right? And it's divided by, let me move it up a little, let me move it up. And this whole thing is divided by x. So this is the same thing, right? I changed tangent to sine over cosine. So let's simplify this a little bit more. The limit as x goes to 0 of this is the same as the numerator, the sine of x over the cosine of x, divided by the denominator. It's actually divided by x, right? Well, to divide by x is the same as to multiply by the reciprocal. So let's just change that to be multiply by 1 over x. Okay, I have a divide by 0 error here still occurring, so it's still a problem. So this is actually equal to the limit as x goes to 0, and I'm going to subdivide this up into the following, into a product, okay? My first product is going to be 1 over the cosine of x, and I'll put it in parentheses, and my second product is going to be the sine of x over x. And my product rule tells me that the limit of a product is the product of the limits. Okay, and I still have a divide by zero error there, and we're going to talk about that in a minute. So since the limit of a product is the product of the limits, then the limit as x goes to 0 of the product is equal to the product of the individual, the limit of the individual facts. So it's going to be the limit of 1 over cosine x times the limit as x goes to 0 of the sine of x over x. And this is the product rule. So now I have to evaluate two separate limits and multiply them together, their product. Okay, so if you look at the first one right here, the limit as x goes to 0 of 1 over the cosine of x, well, the cosine of 0 is 1. So the denominator is approaching 1. So the function is approaching 1 over 1, which is 1. So this highlighted one, its limit is 1. Okay? So let me erase my highlighting and go ahead and put, so 1 times, and now I have to evaluate the limit as x goes to 0 of the sine of x over x. And we've got a problem in this particular case because we're looking at a divide by zero error, right? So in chapter 8, I'm going to talk about something called L'Hopital's rule, but it's actually, we don't study it in this class. That's chapter 8 is where we're going to BC level. But I'm going to explain this to you visually. Because in fact, and I want you right now, to commit this to memory. Whenever you see the limit as x approaches 0 of the sine of x over x, it's going to equal 1. And I'm going to visually show you why. All right? But right now, please, because it's a reoccurring, it happens, you see it, it comes up a lot. The minute you see this, it's equal to 1. Okay? So this is actually equal to 1 times 1, and the answer is 1. So the limit as x goes to 0 of the tangent of x over x is 1. Now I'm going to grab what I asked you to memorize, the limit as x approaches 0 of sine x over x. Let me grab this, and I'm going to copy it. And let me demonstrate to you why it's equal to 1. Yes, Maggie? It is because as x goes to 0, the cosine of x goes to 1, because the cosine of 0 is 1, and 1 over 1 is 1. Well, I think that I'm not asking you so much to memorize this because you can evaluate it with substitution. All you have to do is substitute in 0 for x, and you're going to get the limit. But you can't substitute 0 for x in sine x over x without getting a divide by zero error. So I have to visually explain why this is true. Okay? So let me just add a page below, and I'm going to demonstrate it graphically, and you'll see it. Okay? So what I want to do is I'm going to do a graph of the sine of x. And so let's make the sine of x in red. So sine of x looks something, hopefully I'll be okay with this. It it's a repeating function. It has this shape, right? So here we go. Copy it and paste it. And I just did one wavelength, and then I'm just connecting them. There's a sine function, okay? So in red I have, and of course it has, the domain is all real, so it keeps going on forever. This is the function y equals the sine of x. And now I'm going to graph, that's the numerator, right? Now let me graph in blue the denominator. The denominator is y equals x, which is the identity function, right? So let me graph the identity function. The identity function looks something like this. Oh, hold on. I'm going to turn on my straightener. Makes a better visual. All right, so this is the identity function, and let me straighten this out. Okay. Now, if I draw this correctly, and I'm trying to, what happens is you're going to see that as you get close to 0, I've superimposed these functions on top of each other, right? And as we get close to 0, let me write this down, this is y equals sine of x, the identity function. As we get close to 0, you should notice that, in fact, they have the same height. Right. Let's get in black. as we come in from the left, right? As we're coming in on this curve, let's zoom in on this, all right? All right, as we follow both the red and the blue curve from the left-hand side, aren't they approaching the same height? And as we're coming in from the right on both functions, don't they approach the same height? As a matter of fact, and for very small values of x, positive and negative, all right? Whether maybe it's 0.001 or negative 0.001, really close to the origin. Don't these functions have the same height? So as we approach, let's say we're really, really close. So as we approach 0, doesn't the numerator approach some height? I don't know, we could call it a. Here's the height, a. And if we go out, then a maps to, say, some value c, right? So as we approach c, aren't they both approaching a height of a? They are. And so we could say we're really, really close. They're approaching the same height, and we're getting very close to some height a, and a keeps getting, so we end up with like a over a, right? It's 1. They're approaching the same height. You see that? And since they're approaching the same height as we get really close to 0, we have the same height divided by the same height. It's 1. And it happens until we get to 0, because when we get to 0, we have a divide by 0 error, but that doesn't occur until we get right to 0. And milliseconds before we get to x equals 0, there's actually some height to this function. Whether it's positive or negative doesn't matter, but they have the same height, so we have the same height over the same height. Does that make sense? So it's 1. Okay? So please remember this one. It will reoccur. You'll see it on the AP exam, that the limit as x goes to 0 of the sine of x over x is equal to 1. And could you get your calculators out right now and graph sine x over x? Look at it, and you will see that when x equals 0, the function has a height of 1.